welcome to this channel Chemistry Made Easy by Dr. Modi. Today we are going to see the application of molecular orbital theory to the fluorine and neon. Last time we have seen the application of this MOT to some important molecules such as nitrogen and oxygen. In nitrogen we have found that the separation of S and P orbitals is relatively, compared to fluorine, it is relatively smaller, and that is why the S and P orbitals are undergoing mixing, as a result of which the order of sigma g and pi orbitals is seen to be as usual, which was found in B2 and other molecules. But after nitrogen N2 molecule, the order is changed. The sigma g orbital comes lower energy and pi orbitals goes to relatively higher energy. This kind of change is observed also because of the increasing nuclear charge. In case of, compared to nitrogen, in case of oxygen, the nuclear charge is more, and that is why the separation between the orbitals, that is S and P orbitals, is very large, and as a result of which the order of sigma g and pi orbitals is changed or altered. The pi g orbitals goes higher energy and sigma g orbitals goes lower energy. So because of this there is no much more change in the bond multiplicity, etc., but there is change in the order of filling the orbitals. It is also observed that in case of oxygen, the bond distance, O2 oxygen bond distance, changes depending upon the cation. So cation develops influence on the bond distance. It is majorly seen in case of ion such as O2 2-. But further we have also seen that the oxygen is supported, means it is experimentally found to be paramagnetic, and it is also theoretically proved and supported by molecular orbital theory. This is a great success of MOT. Now we will see what are molecular orbitals shown in case of F2 and what is about its stability. So as we have seen that oxygen, and afterwards the next molecule is fluorine. So nuclear charge also increases in fluorine, as a result of which the S and P level separation again increases. So this increase in the separation of these levels is found to be, say this is P and this is S. So this becomes 27.7 electron volt, which was in, so this is in fluorine, and in case of B2 it is S and P characters, it is very little. So this is 5.7 electron volts. So compared to boron B2, in case of F2, the separation, energy separation between S and P orbitals is very large, as a result of which there is no interaction between S and P characters or S and P levels, and that is why the order remains normal or as expected. Further, we will see that what is the molecular orbital diagram for this F molecule. Say this is the energy axis. This is the energy axis, and we have seen that in case of fluorine, this is about the fluorine. So this is about the atomic orbitals. Atomic orbitals of fluorine, and we can have the molecular orbitals of F2. Then we will see The first levels are Kk and the molecular orbitals are Kk. Then there are this 2s orbital. This is 2s. This is also 2s. So after linear combination, it produces this bonding and anti-bonding molecular orbitals. So this is sigma g. This is sigma star u. So there are two electrons here, and these 2 plus 2, 4 electrons enter into these sigma g bonding and sigma u star anti-bonding molecular orbitals. Now we have these 2p orbitals. So there are these also 2p levels. So these 2p levels after linear combination produces this sigma g. This is sigma g. 2p we say 2p3. Then there are these 2 pi molecular orbitals. So these are pi u. Then there are these pi g star molecular orbitals, and this is sigma u 2pz star molecular orbitals. Now in case of fluorine, we have these 2 plus these 3, 4 and these 5 electrons. So there are also such electrons. So the total number of electrons available are these 5 and these 5, means 10 electrons are available, which can enter into these molecular orbitals like this. So 2 will enter into this, 2 again 4 here, and so these are 6, and we have 10 electrons. So in this way, remaining 4 electrons will enter into these sigma g star molecular orbitals of anti-bonding nature, and this sigma u star will remain unoccupied. Now the electronic configuration of this F2 can be shown in this way. So we have this Kk, then we have this sigma g, 2s, 2 electrons, sigma u star, 2s, 2 electrons, then this sigma g pz we will show here with 2 electrons, then pi u 4 electrons, then we have this pi g star with 4 electrons. So this is electronic configuration, and we can have the bond order of this. So 1/2 of, we will cancel this sigma g electrons with this pi electrons, that is bonding effect is cancelled equally by this anti-bonding effect. So there are 3 lobe orbitals, molecular orbitals providing 6 electrons minus these anti-bonding electrons 4. So we will have these 2/2 means 1. So there is only one FF bond, that is one sigma bond. So here the important thing is that this molecule is found to be very reactive. So reactivity is also depending upon the electronegativity or electronegative characters. Then we will see that what about the neon, any two molecule. So if we change these, we can have these any, and this any2. So in case of any, we have 6 electrons into here, 2p, like this. So p electrons are increased compared to f2, and these electrons will go into this sigma. Now the bond order will tell us what is the bond order in case of this. Bond order shows that 1/2 of these 6 electrons minus these 6 electrons, that is 0. It means there is no bond between any neon atoms. So the molecule as Na2 does not exist. It means this neon is monoatomic molecule, and this is inert gas. So because of this, it is not reactive. So it will not take part in any reaction. So this is about these the F2 and Ne2. The Ne2 molecule may show some existence in transient species, means for a very short period of time, but normally it is not present as Na2 molecule. So with this we have completed the application of MOT to F2 and Na2. Similarly, we have also completed this application of MOT to the molecules of elements from hydrogen to neon. That is first 10 elements and their molecules have seen according to this MOT. So this F2 molecule which we have seen, there is no unpaired electron, therefore it is diamagnetic. So magnetic characters are also observed here. So with this we will stop our discussion here, and we will go to the next point in the next lecture. Till then, goodbye, see you next time. Please subscribe to this channel and press bell icon and the like button also. Thank you very much.